Welcome students to the MOOC's series of lectures on advanced probability theory. This is lecture number 25. If you remember, we were discussing convergence in distribution. That is, if x n is a sequence of random variables with x n having the distribution function f n and f n x converges to f x, where f is the distribution function of a random variable x, then f n is said to be converging to the random variable x in distribution. And we denote it as x n converges to x with this script L, which means convergence in law, and that is how we typically denote convergence in distribution. We are working out on the following theorem. Let x n be a sequence of discrete random variables, each taking values f n k is equal to probability x n is equal to k, when k is equal to 0, 1, 2 up to infinity. And suppose x is also a discrete random variable taking values k is equal to 0, 1, 2, etc., such that f at x is equal to probability x is equal to x. Then if f n x converges to f x, that implies and implied by x n converges in law to the random variable x. Note that this is convergence of distribution, convergence of random variables, whereas this is the sequence of reals f n x, that is f 1 x, f 2 x, f n x, this sequence. And when we are saying f n x converges to f x, essentially it is the concept of limit we studied in real analysis. So, the distinction between this and this should be clear, and this means if and only if we have already proved that if f n x converges to f x, then x n converging in law or distribution to the random variable x. Now, we want to prove that if x n converges to x in distribution, then f n x converges to f x for all x which are points of continuity for f x. Now, since x is a discrete random variable, it has the following CDF: 0, 1, 2, etc. So, the distribution function is going to be a step function, something like this. Below 0, it is 0, at 0, it goes to some height. What is going to be that height? I am telling you, it is coming to 1, at 1, it is also having a jump. Thus, we are getting a step function of this type, where this jump is probability x is equal to 1 or f 1. Similarly, this is f 2, this is f 0, and ultimately it will be 1. This must be clear to you. Therefore, since x n converges in distribution to x L, x, we are looking at points in the intervals minus infinity to 0. At 0 there is a jump, therefore, 0 to 1 open intervals. At 1 there is a jump, and therefore, we are looking at this set of intervals, or we are looking at points which is in the union of these intervals. We want to prove that if if f n x converges to f x, then f n k converges to f k for all k in 0, 1, 2, etc. Proof: consider x belonging to minus infinity to 0. Therefore, f n x is equal to 0 and f x is equal to 0 for all x belonging to minus infinity to 0. Therefore, there is nothing to prove. Now, consider x belonging to 0, 1, and it is given that f n x converges to f x. Now, f n x in this interval is equal to f n 0 and f x in this interval is equal to f 0. Therefore, f n x converging to f x implies f n 0 converges to f at 0. Therefore, we get the result for k is equal to 0. Now, consider x belonging to 1, 2. For all x belonging to 1, 2, f n x is equal to f n 0 plus f n 1 and f of x is equal to small f 0 plus small f 1. We have that f n x converges to f x. Now, we already have f n 0 converges to f 0. We want to show f n 1 converges to f 1. That is, given epsilon greater than 0, there exists n such that for all n greater than equal to n, modulus of f n 1 minus f 1 is less than equal to epsilon. This is what we need to prove. We are given that f n 0 plus f n 1 converges to f 0 plus f 1. Therefore, we know that given epsilon greater than 0, there exists n 1 such that for all n greater than equal to n 1, modulus of f n 0 plus f n 1 minus f 0 minus f 1 is less than equal to epsilon by 2. Because this is converging to this, given any epsilon, we can find such an n 1. Also, we have proved that f n 0 converges to f 0. That is, there exists n 2 for the same epsilon such that for all n greater than equal to n 2, modulus of f n 0 minus f 0 is less than equal to epsilon by 2. Now, let us use the following result. Modulus of a minus b is greater than equal to modulus of a minus modulus of b for any reals a comma b. This we know from our school level mathematics. So, we write modulus of f n 1 plus f n 0 minus f 0 minus f 1 is equal to modulus of f n 1 minus f 1 minus f 0 minus f n 0. So, this is let us call A and this let us call B. Therefore, this is greater than equal to modulus of f n 1 minus f 1 minus modulus of f 0 minus f n 0. Therefore, we can write modulus of f n 1 minus f 1, this quantity is less than equal to modulus of f n 1 plus f n 0 minus f 0 minus f 1 plus modulus of f 0 minus f n 0. Consider n is equal to maximum of n 1 comma n 2, where n 1 and n 2 we have just defined. Therefore, for all n greater than equal to n, modulus of f n 1 minus f 1 is less than equal to epsilon by 2 plus epsilon by 2, which is equal to epsilon. Because we have already shown that this will be less than epsilon by 2 and this is going to be less than epsilon by 2. Therefore, together their sum is epsilon. Therefore, for all n greater than equal to n, modulus of f n 1 minus f 1 is less than equal to epsilon. What does it mean? It implies that f n 1 converges to f 1. Let us now assume that for all j is equal to 0, 1, 2 up to k minus 1, f n j converges to f j. We want to show that f n k converges to f k. Therefore, consider x belonging to k to k plus 1. Therefore, f n x is equal to f n 0 plus f n 1 up to f n k minus 1 plus f n k. Similarly, f x is equal to f 0 plus f 1 plus f k minus 1 plus f k, and we know that f n 0 converges to f 0, f n 1 converges to f 1 and f n k minus 1 converges to f k minus 1, and we also know that sigma f n j, j is equal to 0 to k converges to sigma j is equal to 0 to k f j, and f n j converges to f j for j is equal to 0, 1, 2 up to k minus 1. Hence, by applying a similar technique, we can show f n k converges to f k. I leave this as an exercise. You just have to imitate what I did for 1, and in a similar way you can do it for k. So, this we have proved for discrete case. For continuous case, also we have a similar result, which says that let x n is equal to 1, 2, 3, etc., and x be continuous random variables such that f n x converges to f x for all x as n goes to infinity, then x n converges in distribution to x. Actually, it is not for all x, it is actually for almost all x, but that concept still I have not given. So, let us assume that this is true for all x, and in that case we can show that the sequence x n of random variables will be converging to the random variable x. I am not going to give the proof because that needs more mathematical treatment, but we can accept that result. Show that if x n is a sequence of random variables which is converging in distribution to x, then for any constant c, x n plus c converges to x plus c and c times x n converges to c times x. You can prove them very easily from the definition. I leave that as exercise. Okay. So, let me give you an example, very interesting example to understand the convergence in distribution. So, let x 1, x 2, x n etcetera be IID random variables, each x I distributed as beta 1 distribution with parameter 1 comma say beta. Let x n be maximum of x 1, x 2, x n for all n equal to 1, 2, 3 etcetera. We define a new random variable y n as follows, that y n is equal to n to the power lambda 1 minus x n. Question is, for which value of lambda the sequence y n converges to some distribution f and identify the distribution. Solution: y n converges to some random variable y in distribution if limit n going to infinity f n y is equal to f y of y. Now, f n y is equal to probability y n less than equal to y is equal to probability n to the power lambda 1 minus x n less than equal to y is equal to probability 1 minus x n less than equal to y upon n to the power lambda, which is equal to probability 1 minus y upon n to the power lambda less than equal to x n by transposing the variables is equal to 1 minus probability x n less than 1 minus y upon n to the power lambda is equal to 1 minus probability x 1 less than 1 minus y upon n to the power lambda, x 2 less than 1 minus y upon n to the power lambda etcetera up to x n less than 1 minus y upon n to the power lambda, which is equal to 1 minus probability x 1 less than 1 minus y upon n to the power lambda whole to the power n, since x 1, x 2 etc. up to x n are IID random variables. Now, x 1 is distributed as beta 1 with parameter 1 comma beta. Therefore, if x 1 at a point x is equal to 1 upon beta 1 comma beta x to the power 1 minus 1 minus x to the power beta minus 1 is equal to gamma beta plus 1 upon gamma beta gamma 1 minus x to the power beta minus 1 is equal to beta gamma beta upon gamma beta 1 minus x to the power beta minus 1 is equal to beta 1 minus x beta minus 1 for 0 less than x less than 1 and beta greater than 0. Therefore, f n y is equal to probability y n less than equal to y is equal to 1 minus integration of 0 to 1 minus y upon n to the power lambda beta 1 minus x whole to the power beta minus 1 this whole power n is equal to, I like you to work out on this to check that 1 minus y upon n to the power lambda whole to the power beta whole to the power n. You please do the integration to come to this point. Therefore, if lambda is equal to 1 upon beta, then we have f n y is equal to 1 minus y to the power beta upon n whole to the power n. Therefore, taking limit n going to infinity, we have f n y is equal to 1 minus e to the power minus y to the power beta. Can you recognize this distribution? We have already seen that this is Weibull distribution. Therefore, for lambda is equal to 1 upon beta y n converges its distribution to y, which is Weibull distribution. Okay, friends, this is about convergence in distribution. This is not a very strong convergence. So, there is a stronger version of convergence which is called convergence in probability. Let definition, let x n be a sequence of random variables defined on some probability space omega s and p, x n is said to be converging in probability to a random variable x if for every epsilon greater than 0 probability modulus of x n minus x greater than epsilon converges to 0. For all n greater than equal to some n, where n depends on epsilon, or in other words, given epsilon greater than 0 and eta greater than 0, however small they are, there exists n such that for all n greater than equal to n, probability modulus of x n minus x less than epsilon is greater than 1 minus eta. Note that convergence in probability does not imply that modulus of x n minus x is less than epsilon for all n greater than capital N. So, that is not the implication. Rather, it says that the probability that modulus of x n minus x greater than epsilon can be made arbitrarily small. So, let me give you an example. Let x n is equal to, it takes two values, one with probability one by n and 0 with probability 1 minus 1 by n. To show that the sequence of random variables converges to in probability to the constant 0. So, although 0 is a constant, we may treat it as a random variable x which takes values 0 with probability is equal to 1. So, we need to show that given any epsilon and eta greater than 0, we can find n such that for all n greater than equal to n, probability modulus of x n minus 0 less than epsilon is greater than 1 minus eta, that is probability modulus of x n less than epsilon is greater than 1 minus eta. Consider capital N such that for all n greater than n, 1 by n is less than eta. That is always possible. As 1 by n goes to 0. Therefore, for all n greater than n, probability modulus of x n greater than 0, that probability goes to 1 minus 1 upon n, which is greater than 1 minus eta. Therefore, we can easily see that probability x n is equal to 0 converges to 1. Hence, x n convergence in probability to 0. The following results are true if x n converges in probability to x and y n convergence in probability to y, implies that x n plus y n convergence in probability to x plus y, x n minus y n converges in probability to x minus y, x n y n converges to x y in probability, k times x n converges to k times x in probability, and also if x n converges in probability to x and g is any continuous function, then g of x n converges in probability to g of x. This comes from the definition of continuity, and I like you to prove these results as an exercise. A natural question is, does convergence in distribution imply convergence in probability? The answer is no, and we give you a counter example. Consider a random variable x and a sequence of random variables x n jointly distributed as follows: x comma x n takes the values 0 0, 0 1, 1 0 and 1 1, with probabilities 0, half, half and 0. Say something like this: x n takes the value 0 and 1 and x takes the value 0 and 1, so that this has probability 0, this has probability half, this has probability half and this is 0. Therefore, marginal density of x is equal to 0 with probability half and 1 with probability half by adding these rows, and for x n also it is 0 with half and 1 with half. Therefore, the cumulative distribution function for x is equal to when this is the value 1 and this is the value half, and similarly the CDF for x n is also the same. It takes the value 0 before 0, at 0 there is a jump at half, then it continues like that till 1, then there is a jump and it continues with the value 1 till infinity. Therefore, x n converges in distribution to x. However, probability modulus of x n minus x is equal to 1 is equal to 1. That is, modulus of x n minus x is always 1. Hence, x n does not converge in probability to x. Therefore, convergence in distribution does not imply convergence in probability. However, there are two things to know. One is that convergence in probability implies convergence in distribution, and two, there are special cases when convergence in distribution, that is x n converging to x in distribution, implies convergence in probability. Okay, friends, I stop here today. In the next class, I shall prove this result, and also I shall introduce you to some stronger versions or stronger modes of convergence for random variables. Okay, friends, thank you so much.